Okay, so I don't know why it keeps on moving, but so hopefully you responded to that last question. So what happens when we put an electron in an electric field is it's going to feel a force. This electron, if we kind of just place it in there, we said a bunch back when we were dealing with electric fields that it's going to feel a force and going to want to move towards, oh, that was a terrible straight line, towards this positive side of this plate. So it's going to feel this electric force that is upwards. And then the same time from the first part, from our left-hand rule, because we're dealing with electrons, we said it's also feeling this magnetic force downwards. So this is really interesting. We have two forces that are acting in opposite directions. So we have the electric force acting up, and then we have this magnetic force acting down. And eventually what's going to happen is these forces are going to strike a balance, and our electrons will be in equilibrium. And that's kind of our key to helping us derive equations and figure out what's going on with that. So I'm going to be referencing this book because I'm really bad at deriving equations, so that's what I'm doing if I'm looking over here. But so back when we were dealing with electric fields and all that good stuff, we got this equation that told us, I should have found this ahead of time, the electric field is equal to Q, so that charge, in this case the charge of our electron, times the value of the electric field. So let's start from there. Let's start with this idea that our electric force is equal to Q, the charge of our particle, times the electric field. So we're starting with that idea, and then we also said in this case, eventually we're going to reach this point where the electric force and the magnetic force equal out. Those things become equal to each other, and that electron is going to be kind of in this equilibrium. So it's also going to eventually equal our value for our magnetic field, or the force of the magnetic field, so this FB, this F magnet. And we said before that this magnetic force equation is Q times V times the magnetic field. So we really have this Q times E equals Q VB, where this V is the velocity of that moving conductor. So this V is the velocity. That's going to be important. So this V is the velocity, and then we have Q on both sides dealing with the same charged particle, so we can say E is equal to the velocity of that moving conductor times the magnetic field. So that's a really big idea. And then what we're going to say, this is a little bit tricky, but so we also have this relationship between the potential, so that V, that voltage, that potential, and the electric field. And we said that that relationship was that E equals V over R. So that R is that separation between the plates, and then this V is the potential, and this E is our electric field. We said a lot when we dealt with potential that was this function of the position. So the position matters. This position within this field matters. So it's this function of its position, this spacing between the plates. So we're going back here. So then what we can say is, well, we kind of have this E equals V over our spacing. This V in this case is voltage. I'm going to make kind of this potential difference, this capital V, this V over that spacing between our plates. We're saying like, hey, we have this conductor of length L, so we're going to call that L. So I can sub this in, this potential over L equals our velocity times B, and then I can solve this for our potential, say L VB, and I can rearrange it. No, actually that's how we want it. But so then what we're going to do, our last little step, just to avoid some confusion, because we're dealing with this voltage and this velocity, we've been kind of saying sometimes that we can represent this voltage in a battery, or because of charge motion, as this E. Oh, that was not a good fancy E. Kind of this fancy. You can draw it however fancy. Oh my god, now I'm freaking out about it. Jeez. There you go. So we have this fancy E, this EMF. That's what it stands for, electromotive force. So this potential difference because these electrons are being physically forced. So we have this EMF. It's the same thing. It's just another representation of voltage. So you can think of this potential difference. So you can think about it as V or you can just think about it as this electromotive force, this potential. So it's the same as a voltage, L, V, B, where V is the velocity of that moving conductor. So now we have this idea that we have this voltage, we have this potential difference because of this motion of a conductor. So this is big because we said, oh, we have this current. This is kind of leading us to see, where did this current come from? This current is happening because we have this potential difference. We have this electromotive force. So this is really like we kind of just created a battery. By moving this conductor through this magnetic field, we have this push on these particles. We've effectively created something that has a potential difference, just like a battery does. So we said, hey, this current is induced, and that's really because we have this voltage. So that's where that current is coming from. It's because we have this potential difference between our particles. And this is one of our equations. This shows up on our equation sheet, that this electromotive force, this potential difference, is, it's all the way at the bottom, I think, equal to the magnetic field times the length of the conductor times the velocity. And they won't ask you to do it, I don't think, directly. It's not one of our equations on the actual sheet. Oops, I don't want OBS. So it's not an actual equation, but what we can say then is, well, if we have some sort of wire, we know that V equals I times R, or in this case, if we're looking at this potential equals I times R, we can use this to figure out like how much current we are moving, how much current we are dealing with. So we can say, if we want to solve it for I, it's fancy E over R equals LVB over R is equal to our I. So we said that when we have a changing magnetic field, or when we're changing our magnetic field about an object, we induce this current. So this is our ability to figure out an equation for how much current we are inducing. So what is our value of that induced current? We're getting that current because we have a potential difference because of that charge separation. So we have an ability to figure out how much current we are inducing based on this kind of thought process, this logic, and our V equals IR, this Ohm's law. So hopefully that wasn't too rough, but now we have this new equation that we can work with. So we're going to get some new information next, but that's kind of the trickiest stuff we're dealing with. The rest is a little bit more straightforward. So hopefully that makes sense, and I'll see you in the next video.